Alright, here we are back with Algebra 1. We're looking at section 2.8 in the book, Proportions and Similar Figures. Our essential question is, how can you find the missing side lengths in similar figures? Okay, I guess we should start out by talking about what do we mean by similar figures. Okay, a similar figure is a figure with the same shape but not the same size, but they're proportional. It's like you looking at a picture of yourself. Everything, it looks exactly like you. Everything's proportionally the same, but it's not the same size. Okay, it's shrunk down or it could be expanded. Another good example is scale drawings, maps. When you look at a road map, okay, your GPS, they're not exactly the same size, but they're proportional. Those are all examples of similar figures. Okay, so they're proportional. The symbol we use is this wavy line. Okay, that means similar. It means they look the same, they're proportional, but they're not always the exact same size. If they're the exact same size, you'll learn next year in geometry they're what we call congruent. Okay, so here's an example of what it would look like. We have triangle ABC here, and we're saying that it's similar to triangle FGH. What does that mean? Well, what it means is that if you looked at what we call corresponding sides, where AB would correspond with FG, that if we wrote that as a fraction, the length of AB over the length of FG, and then the length of BC over the length of GH, and the length of CA over the length of HF, they would be proportional, they'd be equal. Okay? If you're going to take one side and double it, you have to double the length of all the sides. Okay? Or if you cut them into a third, you got to cut all of them into a third, otherwise it looks cockeyed and it's not, it wouldn't be proportional anymore. So if we took their lengths 8 over 12, 12 over 18, and 10 over 15, and you notice I kept this triangle over this triangle. Yeah, and once you set it up, and it doesn't matter which way you do it, you have to stay that way. Okay? You can't take the length of triangle 1 over 2 and then go 2 over 1, because you just messed up your proportionality there. So 8 over 12, does it equal 12 over 18? Does it equal 10 over 15? Yes, they all equal 2/3. And that 2/3 is what we would call a scale factor. Okay, again, something you're going to see a lot more of next year, but that's a scale factor. Okay, so what they did is they took this triangle and they blew it up 2/3 or 1/3. Okay, or you could say this triangle is 2/3 of that triangle. That'd probably be a better way to think of it. Okay. Let's look at another example here. If triangle ABC is similar to triangle DEF, then, let me get a little bit better here. There we go. Find DE. So this is what you're given right here. Here's ABC, here's DEF. They tell us that AB is 10 and that BC is 16. Over here they tell us that EF is 12 and DF is 18. Okay? The thing to know is this. DE, what does it correspond to in the other triangle? DE, it corresponds to AB. Okay, that's going to be important. So I'm going to take this triangle over that one. You can do it the other way, that's fine. Just again, keep that same relationship all the way across. So I take AB over DE, then I'm going to set that equal to, I'm going to pick a pair of sides of the two triangles that correspond that I know their lengths. Okay, as long as I know their lengths, then I have a fraction to work with. Okay, so I chose BC and EF. They correspond. BC is in the same place as EF, so that's why I picked this one, because we know this ratio, so that's why I picked it. So here I go. I plug in what I know. AB is 10. DE is what I'm looking for. I know that 16 over 12 fits in for that ratio. So once I get this, it's cross multiplying. It's a proportional. Two equal fractions, what we did the other day. Cross multiply, 10 times 12 is 120. 16 times DE, you've got multiplication here, so divide out the 16, it goes in there 7.5. So that's the length of DE. Okay? So that's how you find the side of a missing, or the length of a missing side. Kind of what we were looking for in that original question. Alright? Look at two other application type problems here. we have the sun up here, and it's shining down, it's casting a shadow. For this building here, and we don't know the height of it, that's what we're going to want to find, it casts a shadow of 15 feet. And we know we have a 5-foot tall person here, and at the exact same time they'll cast the same shadow, but this shadow length is 3 feet for the person. Okay? But things are proportional here. You've got the same angle, same line of sunshine here coming in, so we can set up a proportion with this triangle and this triangle. Okay? Shadow length over shadow length, so I'm going to take little to big. So for me it's going to be 3 over 15, because that's what I know. That's the ratio I know. I know both their shadow lengths. Okay? I know the height of the person, but X, the height of the building, that's what I'm trying to find. How tall is that building? Okay? So proportional, height over height, shadow length over shadow length, and I went little big, little big. So I've set up my proportion. Once you do that, boom, boom, cross multiply. 3x equals 5 times 15, which is 75. Got multiplication, so divide it out. Oh, I'm sorry, that's 25. So our building is 25 feet high. Okay? And you kind of think of it. The shadow length of the building is 5 times more than the shadow length of the person. So the height of the building should be 5 times more than the height of our person. 5 times 5 is 25. So that works out. So that's an application of similar figures and proportional, showing them proportional. Another one here is anytime you look at a road map, okay, which kind of with GPS and computers is getting kind of outdated, but maybe you've seen a fold-out map somewhere. So what is the actual distance from Jacksonville to Orlando? We have this map laid out, and it's problem 3 on page 145. This one was problem 2 on 144. They tell us that the map scale, and if you look on that map when you hold it out, somewhere on there it'll tell you, in this case it's 1 inch equals 110 miles. Okay, that's the scale of the map. So every time you measure an inch on that map, it represents 110 actual miles. When we measure from Jacksonville to Orlando on our map, we get 1.25 inches. Okay, so if you kind of think about it, you got Florida laid out here. Here's Orlando. Here's Jacksonville. I know that's a good picture, good drawing. Okay, we measured this distance right here to be 1.25 miles. So we want to set up a proportion to figure out what's the actual mileage here. Well, our scale, our map scale, gives us the ratio that we need, that we know, and it's 1 inch represents 110 miles. Now I write in the units here just so you can see that I'm going inches over miles, and I'm going to do the same thing over here. I know the distance in inches that I measured on the map was that. What I want to know is the actual miles, and I'll call it X miles. Okay? You can see already we're going to cross multiply. Okay? 1 times X is X. 110 times 1.25. It's 137.5 miles. Yep, right on. Okay? That's the actual distance. Okay, so we got a couple different ways of looking at using proportions to solve lengths of sides of similar figures, whether it be something like this, or on a map, or if you're given triangles or objects like that you want to look at the relationship between the lengths of the sides. It all comes back to them being proportional. Similar figures are proportional, so we set up a proportion, which we know is 2 equal fractions, and we know we can solve them by cross multiplying. Okay, that's all the stuff we did in the last section. So we're just kind of tying it together, bringing some things together here, looking at a little bit more application of this. When you come into class, we'll pick up from here and look at solving some more proportions and get into the application of it. Okay, hopefully this has been helpful. Got any questions, bring them with you tomorrow, and we'll get them answered. All right, you guys have a good one. We'll see you then. Bye.